Welcome to EvolvNext, and let's explore NumPy library in detail. In this video, what we will cover is the introduction to NumPy library, then why do we use NumPy, what are the attributes and operations of NumPy, then how do we index, reshape and manipulate NumPy arrays, how do we broadcast NumPy arrays, and then how can we do image manipulation using NumPy. So if you are someone who is struggling with basic concepts and wants to have an insight on how to code in NumPy, this tutorial is for you. To start with, what is NumPy? NumPy stands for Numerical Python, and it's a library for Python which adds support for multidimensional arrays and matrices along with large collection of high-level mathematical functions to operate on these arrays. So this is formal definition of NumPy. However, I would like to give you a background of what prompted this NumPy library to be there in Python. Look, C has a concept of an array, okay, and NumPy has got Python has got lists, that is Python lists. Okay, now as Python is not that fast as C, what was decided that maybe we can use the speed of C and the data structure of Python, and why not combine them together? And that's where NumPy came in. This library is made in C and Fortran, and we are just using it in Python. So let's first see what is the difference between Python list and NumPy arrays. Okay, so it's an array. It will store homogeneous kind of data type. For NumPy array, it stores homogeneous a data type, that is all the elements in that array will be of same data type. And NumPy is specially used for, most of the times it will be used for numerical analysis, so you will find out the data type most of the times as numbers. Okay, and in Python list you can store heterogeneous data types. You might have seen our course for Python beginners where I have talked about list. Then performance wise, NumPy is much faster. However, Python list, when they are exposed to large data sets, performance dips down. All right. Memory wise as well, NumPy arrays are more efficient as the way what you can say elements are stored in a contiguous manner. And in Python list, the memory may be the elements in the memory could be stored in scattered locations. All right, and if you say functionality wise, then NumPy arrays have a lot of mathematical functions involved, and in Python list there are limited built-in operations. So that's about the difference of NumPy arrays and Python list. We will also see how efficient it is time wise when we do this coding exercise while we create new NumPy arrays. Now in NumPy arrays, there is only one data type, that is ND array object. ND array means n-dimensional array. Okay, it's a core part of NumPy, and let's see how we can create those arrays. So before creating those arrays, I would just like to tell you that NumPy doesn't come installed with Python. You have to install it separately. It's a different library. You will have to install it separately. Say in some platforms like Anaconda, it may come installed already. However, if you are doing code on your machine using some IDE, you might have to install NumPy. And to install NumPy, this is the command we already know. Okay, pip install. Now, um, after installing, you will have to import that NumPy, and you'll have to also specify an alias name, though not a compulsion. However, when you will be using this word NumPy, or you will be using NumPy while you code, right? So you don't want to use this big word. Instead, you just give an alias name, and use that alias name while you create some array objects or do any NumPy operations. All right, so let's see how you can create a one-dimensional array in NumPy. So I've taken a variable arr, and in that np dot array is the function that I'm using, and I'm passing a list into that. This will create an array for me, one-dimensional array. So I will just run this cell. You would see array being created, and it will show it to you as a array object. Let this run, and we will see the output soon. All right, it gives me an error because I did not run the first cell. I have to import the NumPy.
library. Now I run this and now I will get the output. Look at this. An array object is being created. You just created an object that is one dimensional array object. All right. Then next, similarly, you can create two-dimensional array as well, using what? Using nested list. You put a list inside a list, and that too inside a array function from what? NumPy library. So np.array, and you have just entered list inside a list, and that's your 2D array, right? Similarly, multiple 2D arrays will be nothing but your 3D arrays, and so on. You can go on just creating multiple dimensional arrays. So I'll just run this cell for you, where you can see 2D array and 3D array being created. So this first output refers to the 2D array, and this output, second output, refers to three-dimensional array. All right. So moving forward, let's see. We earlier we talked about, when we talked about the difference. I said that its NumPy arrays are much more faster than Python lists. So just to demonstrate that, we have something called as time IT. All right, and with that we will see how, what is the time that is required when you do some operation with a given range. I have taken some, say, 10,000 numbers, and I'm trying to calculate squares of those numbers. So let's see which of the list, or sorry, which of them, like either the list does it in a speedy manner, or does array do it faster than list. So for that, I have created a list. I've assigned a range of 100, and then I'm with this time it, I'm trying to do, I'm trying to calculate the time that is required for calculating squares of all those numbers. So they have applied a for loop. So basically they are using something called as list comprehension, and they have applied a for loop, and they are trying to calculate a square with this code, and we are trying to see how much time does this operation require. Now if you look at the output, you would see that we took around 2.77 milliseconds to calculate square of each number from 0 to 9999. All right, and when we do the same in array, all right, here you created an array object, pass the same range, and you are doing the very much same operation. You don't need a for loop here. It's a straightforward calculation, just squaring. It will when you write this, it will just square each and every element inside that array. Now let's see how much time does this take. And bang, you will see a lot of difference in the time. Here it was milliseconds, and here it is microseconds. So can you notice it's that efficient in terms of calculation? That's the reason NumPy arrays are preferred over the list when such calculations come into play. All right, now let's see. This is something I think we have already seen, creating 2D arrays. Now there is one another way to create an array, arrays of ones and zeros. All right. So if you want to create an array which has only ones, so we have ones function in NumPy library which can be used, and we just need to mention what number of rows and number of columns. So 3 is number of rows here, and 4 is number of columns. And if you run this, you will see arrays of ones is created, and the whatever number we specify in rows and columns, it will take it here. If I want 4 by 4 or 5 by 4, it will do that way. So this is how it will just create arrays containing all ones. If you want arrays containing all zeros, your function will change to zeros. So as we have it for one, we have it for zeros as well. Then we also have a random function in NumPy. So the syntax, or the way we write, is np.random.random and 3 comma 4. All right, when we write this 3 comma 4, again is what? Rows and columns. If you notice, the numbers that are generated here, okay, are do lie between what? 0 to 1. Okay, and there will be float numbers. So all the any random floating numbers would be generated from 0 to 1 using this random. So this is one another way. Now np.linspace. Now what will this function do? This, if you notice, we are giving a range like we used to give in for loop. Okay, we used to mention range. I mean, I hope you are aware and able to recall what range function did. We specify the starting point, we specify the ending point, and then we give the step size as well. Here, instead of step size, we are saying how many number of elements you want in that particular range, in the sense that we are starting at -5, we are ending at 5. All right, and how many number of elements you want in that, that is what we are mentioning here. This is not a step size. instead we are mentioning how many. So I want 10 elements between 5 and 5. So let's see what happens uh, when we execute this. So when we execute this, we get 10 elements, and those are equidistant. In that 10 elements, the consecutive elements are equidistant from each other, in the sense the difference between 3.888, this number 3.88888 and 5 will be same as the difference between these two numbers. These two will, the difference between these two, in the sense the difference between the consecutive numbers will be the same. Difference between these two, difference between these two. So they are what? They are linearly spaced, meaning the consecutive numbers are equidistant from each other. Just to prove my point, I will just mention. I will just show it to you. We will calculate the difference. I just calculate the difference. 5 dot minus 5.0 minus this number, right? So just to cross verify what we are trying to say when we talk about the lens space, okay? Then after that, what was this? Yeah, 3.889 minus 2.77778. Okay, that is what. You would see the difference between the consecutive elements is identical, and it takes care of the difference to be identical. Any number you mention here, if I mention 20, again it will do the same thing. Difference might change, it will not be constant always, okay, but it will be same, or you can say it will be identical between the consecutive elements of that particular array. So that's how you use lean space for creating what? Creating a linear spaced array. Then after that, there is something called as np dot identity. Now this is used to create an identity matrix. Now what is identity matrix? I'll just run this, then you will be able to recall. This is called as identity matrix. I did not mention rows and columns this time, because in identity matrix, your rows and columns are same. You don't need to mention separately for rows and columns. That's why they just took one parameter. So if you mention 4, it will create 4 by 4 matrix. If you mention 5, it will create 5 by 5 matrix. And after creating that 5 by 5 matrix, it will create identity matrix, meaning the diagonal elements will always be what? Always be 1, and other elements are zeros, and that's something we call as identical matrix.
Now let's jump in next topic.
Here we will have a look at few commonly used attributes and operations in NumPy. So let's start. First, we will import the NumPy library as we did in our last session, and we will create array. Here I have created two arrays, and then we will check the attributes that are associated with NumPy arrays, right? So here I'll just run this initial cells, and then we proceed to check all the attributes. So if I do a dot endim, what does endim provide us is that it provides us with the number of dimensions of an particular array. So I just will clear this outputs so that you're not confused, and we will see the output each for each and every cell. So a dot endim, if I write it a dot endim, it will give me number of dimensions of that particular array. So look at this. When I do a dot endim, it gives me that it's a one dimensional array. If I do capital B dot endim, I could easily see it's a two dimensional array. Alright. After that, if I do a dot size, then what size will it give me? I'll just run it. It will give me 5, because there are in all 5 elements. If I do a size of capital array capital B, so B dot size, oh, B dot size, what does it gives me? 4. All right, because in all how many elements I have? 4. That's the reason it returns me 4. Now I will go one step ahead, and I'll check b dot item size. Now just make a note, what is the difference between size and item size. Now item size, this depends on the data type, and the memory required to store that particular element on depending on what is the data type. Now if you could see in B, what do we have? We have integers, or in A we have what? We have float values. Alright, so it took 8 bytes to store that, and this size is in bytes. Alright, if it was a boolean value, that's the reason I created one boolean array. And if it was a boolean value like true, false, and true again, here I created an array. Now if you look at the item size for this boolean array, then you would see the item size is what? 1, because it allocates only 1 byte to for storing the boolean array. Okay, now moving ahead, a dot shape, this will return the shape of an array. Okay, exact shape. So it will tell you how many number of rows are there, how many number of columns are there. So for A, it is one dimensional array, so we had 5 columns. That's the output that it is showing over here. Now if we do B dot shape, okay, so in B dot shape it will show the output 2 by 2, because B was a 2 by 2 matrix which had 2 rows and 2 columns. Okay, after that we will um, see what is D type of array A, what is the data type. So we get it as float 64. Please remember, what it is showing here is it is showing the data type of each and every element. This whole array is of data type float. That is what it is trying to convey it to us. All right. So that's all about the attributes. Now we jump into the NumPy operations. In NumPy operations, we will have a look at what arithmetic operations are possible. So I've created one array. ARR is equal to np dot array, and I've just passed 3 elements in that. So when I do addition by 10, what will happen? Element wise, the addition will be done, and in every element 10 will be added. Similarly, if I subtract something, in every element, whatever I subtract, that subtraction will happen. Similarly, for multiplication as well, only thing is that the operator will change, that is, it will use asterisk. And then for division also the same way. The thing to show here is element wise it does the operation, and so on you get the output. All right, after that I've just created 2 arrays this time, to demonstrate the dot product operation for arrays. All right, so what is when is the dot product possible? In first case, if there are 2D arrays, the number of columns in the first matrix should match the number of rows in the second matrix. Only then we will be able to perform dot product. That's the reason, for simplicity, what I have done, I have taken A and B as 2D arrays, and I have what I have achieved with that is the number of columns in first matrix, so that is 2, because I have 2 by 2 matrix, and number of rows in second matrix, that is also 2, and that is identical. So for simplicity I have just kept all the number of rows and columns same, so that we can see how this result is achieved. So we have np dot function by which we can do this operation of dot product. Now if I run this, you will get the output as 1943, 1922, 4350 respectively. That means I will just explain a little more on this, the way the calculation is done. Okay, so the way calculation is done is this way. Okay, first row and first column, first row from matrix A and first column from matrix B. Okay, so if you would see here, first row 1 into 5, that is 5, and 2 into 7, that is 14, and 5 plus 14 is nothing but 19. Similarly, again first row and second column. So what is there in first row? 1 into 6, the multiplication position wise, and 2 into 8. So that turns out to be 22, and so on. We get the output 1922 and 4350 in a 2D, two-dimensional array as a resultant matrix. Okay, so that's how the dot product operation is carried out. Then we even move further to check if we can do a comparison operator on a NumPy array. Yes, we absolutely can, because let's see first what is there in ARR. Is there something that we have defined as a ARR? Yeah, we have 1, 2, and 3 in ARR. Okay, so in ARR, if I do ARR greater than 1 element wise, it will compare as it did addition, subtraction element wise. Here also it will compare element wise, and it will return a boolean array. I say it boolean array because you would see here the array that is returned has only values what, false and true, right? So that is boolean. And then we have some more operations like mean, max, sum. So here I have not run all of those, but I am just showing it that if you want to sum, if you want to do a sum of particular array elements, then you can simply use np.sum and you can do it. And np.mean will give you average of the elements that are there. So the sum turned out to be 6, that is 1 plus 2 plus 3, because ARR was what? ARR, hold on, I will just um, display ARR here. In ARR, we had three elements, 1, 2, and 3. And what is the sum? It will turn out to be 6, and that's what they expected. And mean will give you average, that is 6 by 2, 6 by 3, that will turn out to be 2.
Now let's jump in next topic.
I would just create a simple NumPy array and do what? I would like to only print first four elements. Then what I would apply? I would do slicing using indexing, the way I did for lists and for that matter strings in our basic course. So the same way you use the index will start here as well, from number 0 and 0, 1, 2, and 3. So number 4 will get excluded, that is the index 4 will get excluded. All right, so the result you get is 1, 2, 3, 4. Then if you want to use negative indexing, you can use negative indexing as well, and you can start at -5. Here it is -5 minus, um, which number is at -5? Let's have a look. -1, -2, -3, -4, and -5. So it will start at 3. And what number is at -7? It is 1, right? So -7 will get ignored, and it is going in the direction of -1. So it's negative indexing. So only 3 and 2 will be displayed. Similarly, if it traverses in opposite direction, you will have to mention 1 over here. So -5 to 1, and then increment by 1. So you can whatever size you want, you can put it over here, as this is parameter for step size. So it's very much the same indexing that we used in strings and list. All right. Now let's move on to the concept of Boolean array. Now suppose if I want to write array, I'm using a range function here. So as it was a range function in Python, here in NumPy we have a range function which allows you to insert a step size of decimal numbers. Suppose if you want to create an array of decimal numbers and you want to give a step size of, say, I'll just show it to you over here. Suppose you are creating one array in range, say np dot a range here. Then you want to insert a decimal number as a step size. So you are say starting from 1 going to 5, and you want to insert a step size of 0.5. So if you do it via simple function range that we use in our for loops, this will not proceed ahead. I mean, that will give you an error stating that it will ask to give an integer value. However, with a range you can give a float value step size as well. So here we are using a range, not really utilizing the float value, but I'm just telling the difference. All right, because you might see that a range is a new thing. Now ARR is equal to, I'm creating an array, and I'm creating an array of range from 1 to 15. Now if I print ARR, then what would I get is the array from 0 to 14, right? And look at this. When you execute ARR less than 6, you got some different array, and that array has got values as true and false. And this kind of array that has values only of trues and false is nothing but called as a Boolean array. Look at the way the comparison is done. Comparison is done on element to element basis. Okay. So after this what we will do is whatever. I think this is something that we saw in our earlier videos when we saw comparison operator. Now using this boolean array, what we will do, we will run that boolean array on our original array, and this is how you run it. This is the syntax. So arr, in the bracket you give the condition, and the resultant array that you will get will be of only true values. So let's just have a look at it. Look at this, true values. Our original array had 0 to 14 numbers, or you can say 0 to 14 elements. All right, and what is the output that we got is from 0 to 5, because in this we had mentioned arr less than 6. So I said the true values will be written. You can see only for first 5 positions there are true values, that is 0, 1, 2, 3, 4, and 5. And from next I mean from 6 onwards, the condition doesn't match and it has false. That's why I said that only true values will be written. This concept is called as fancy indexing, or boolean indexing. It's a MOOCs, even they will call it as maxing, so no need to confuse. These are all the same terms. Now just tweaking around on the conditions. All right, so if I say I want only I want only even numbers from the above array. So I would just write the condition for the even numbers, and I will run it through on the original array. Wherever there are true values, those will be written. That's the reason I got the array of even numbers. Similarly, I can have a combination of conditions wherein we are now checking the numbers that are divisible, completely divisible by 2 and completely divisible by 3. That's the reason we have used modulus 2 and modulus 3, and we are expecting their modulus to be 0, that is the remainder to be 0. And what we are trying to return is an or condition. If you have a look at it carefully, I'm using bitwise or and not the and or operations that we normally use. I'm using a bitwise or here. The reason is whatever the combination I'm trying is I mean whatever the combination of conditions I'm verifying upon is nothing but a boolean array. That's why I'm using bitwise operator. Okay, so you would get a result of all the numbers which are divisible, completely divisible by 2 or are divisible by 3. Okay, so this is nothing but just for your understanding, so that you are aware that these are the true values that were written, and using or condition, if any one of them is true, those were written. After that, I'll just run a ARR again so that you don't have to go back and see. And np.where, now I'm using a where function. What it will do is returns the indices in tuple. Okay, so if I do arr less than 5, it is not going to actually return the values. It will be returning the indices. That's another thing, that here the values and the indices are the same. However, it is returning the indices. Okay, so if I run this, you would see arr less than 5. Um, so these are the values till here. Just hold on, less than 5. So till here these are the values which are less than 5, right? So what it has done is it has returned the index of those values. Okay, not the actual values. Now if I want to further enhance, or you can say further I want to use utilize more functionality from the where function, what I'm trying to do is wherever, at whichever index you get arr less than 5, just specify the original value, keep it as it is, and which are not, you please increment it by 1. That's the result I'm expecting. So the result I'm expecting is 0, 1, 2, 3, 4. All right, and from 5 onwards I will add 5 to each and every element, that is 10, 6 plus 5, 11, 7 plus 5, 12, and so on. So let's see if I'm getting the result. So you might treat this like if else condition that we studied in control statement. So the if the index value is less than 5, keep the actual element as the same element that it was original, else change it and add 5 to it. So let's see if we achieve the expected result. Yes, and that's it, we have achieved the expected result. Now let's move on to the next section. Can we perform an iteration on a numpy array? Yes, you can very well do that. It's just for showing it to you that this operation is possible as well. All right, so we can iterate on a numpy array. And now let's jump into our next section, that is array manipulation and reshaping. How do we reshape, or how do we manipulate arrays? So the same function I have used np.arange. This time I'm reshaping and with np dot arrange arrange 12, I will get 0 to 11 elements, right? I mean 0 to 11 numbers, and that will be in one dimensional array. However, I want to reshape into 3 by 4 matrix, and that's why I have used this reshape function, and with that reshape function I will be able to reshape the existing array. This is the repeated statement. I don't need it anyway, so I'm just deleting this one, and I'll show it to you what is the value in ARR1. You can easily see the I have reshaped using the arrange function. I took the range from 0 to 11, and using reshape I created a 3 by 4 matrix. Now similarly I can create, and now I'm using random.random function to create a 3 by 3 matrix. Now here I can create 3 by 3 matrix of numbers between floating numbers, and that is float numbers between 0 to 1. All right, numbers between 0 to 1 of float data type. Now what I'm doing is I'm taking the floor function, okay, and I'm creating a 2 by 3 matrix and multiplying it by 100. So if you look at this output clearly, so when you use floor function, we all know that whatever is after decimal point will be removed. Okay. And what has happened? We have multiplied it by 100. That's the reason we are getting this output as 20 dot something or something else. The random, we all know the random function generates what? Generates the decimals or the float values that are between 0 to 1. But however, we multiplied it by 100. That's why we got 20 dot something, 88 dot something. Okay. And the with the floor function, the rest part was ignored. Okay. Now moving on to the next one. I think transpose is something that we'll see later. So I'll delete this from here. Now let's have a look at flatten and ravel. Now we saw how to convert from 1D to the 2D or 3D, whatever dimensions we wanted using the reshape function. Now if we want to convert a 2D array into a single dimensional array, then how do we do it? We have two functions. One is flatten and another is ravel. All right. So if you look at this, flatten function and ravel, both are giving exactly the same results. What they are doing, it's a 2D array that we have. In the first row we have 1 2 3, and in the second row we have 4 5 6. However, it has flattened that this 2D array to a one dimensional array. So for flattening we have these two functions, ravel and flatten. Now to move on further, we have array 1 and array 2, right? So let's see how we can perform row wise or column wise aggregations, because what we are looking at is manipulation and reshaping of arrays. So let's see how we can manipulate the values using the row wise and the column wise addition for the given arrays. So here I have defined one array. Okay. In this array you could see there are 9 elements altogether, and it's a 3 by 3 matrix. Okay, that is 3 rows and 3 columns. When I do np dot sum array 1 and I specify axis is equal to 0, so what is this axis is equal to 0? It will aggregate on data across columns and sum the value of each column. In the sense, across rows it will aggregate the values across rows, that is this rows, these are the rows, and sum across columns, right? Sum the values of columns. So 1 plus 4 plus 7, 2 plus 5 plus 8, and 3 plus 6 plus 9. So that would give me what? That would give me, for the first column it will give me 12, for second it will give me 15, and then 18. So it sums the values of each column when you specify axis is equal to 0. And similarly, when you specify axis is equal to 1, it will sum the values of each row. 1 plus 2 plus 3, that is 6, and so on. Okay. And we will be using, we have two arrays here, and we'll be using to stack the arrays. We'll be stacking it horizontally and vertically. By that I mean I will be using a stack method, and you would see array 2 got stacked horizontally with array 1. So this was till here 0 1 2 3 4 5 6. This was our first array, and this is our second array. This has got stacked horizontally, and then we have vstack function where it will stack vertically. Look at this. This was our first array, and this is our second array. So the second array got stacked vertically with array 1. Okay. Then we have something called as h split and v split. Like we do stacking, we can split the arrays into number of parts possible using h split and v split. H split is for horizontal split, v split is for vertical split. So in h split, what has happened here is we are trying to split array 1 in how many parts? We are trying to split it in four parts, because four parts, either we can split array 1 in four parts horizontally, or we can split it into two parts. So I'll take two here, and let's see how the splitting happens. Okay. The reason is it is a 3 by 4 matrix. So it has four columns and we are splitting it vertically. So what has happened is essentially, if you look at this, this was the array, right? It has split over here in two parts. That is 0, 1, 4, 5, 8, 9, one part, 2, 3, 6, 7, and 10, 11 as one part, right? And if you want to vertically split it, we have three rows. So there is only one way we can split. That is we can split only one way. That is what? We can split in three equal parts, that is three rows, because we have three rows, we cannot split it into two. That's why I said whatever parts are, whatever equal parts we can split uh, is possible. Only that we can do. We cannot do it in point 0.5 or something. That split will not happen. Okay. And then how can we transpose a given array? So for that we have two methods. One is dot t, and another is one is dot t that will be used with array. So here the array name is array underscore 2d dot t, and the another one is we have np dot transpose function, wherein you can pass the array, and in both the cases you will get the same result. Look at this. This is the result that you have got. So it is, both of them are um, of type nd array, and you are able to successfully transpose the given matrix.
Now let's jump in next topic.
Broadcasting in NumPy is its ability to perform element-wise operation on arrays, even if they are of different shapes, or maybe they are of different dimensions. Even then, without reshaping, we can just try to match them each other following some rules that are these three rules, which we will see one by one. I have just stated it here so that you are theoretically aware of the rules. So let's jump into our discussion and how the broadcasting works. Okay. Um, Here you could see this image. In this image there are three parts to it. I have shown the addition of two arrays where the shape of both the arrays match, and we are focusing on what result do we get when we add. Then there is a second array where the shape is different, like it doesn't match, or you can say number of dimensions are different. Here we have two dimensions and here we have only one dimension. So how do we do addition, and how is the addition performed in such cases? By using broadcasting. And then there are two addition of two arrays which have different shapes. In that case, how does the addition gets performed? These are the things that need to be answered, and this addition gets performed with something called as broadcasting. All right, so let's have a look at this additions one by one. I have replicated exact same thing in our code, that is exact same matrices I've replicated in our code. So let's jump into the code. As usual, I import a NumPy library first, then I would create an array that looks like this: 0, 0, 0, 10, 10, 10, 20, 20, 20, and 30, 30, 30. So I use a type function and an arrange function to construct this array. So if I run this, I would get this array, and after doing a transpose, I'll get the array that is there in our diagram. So in first row it's all zeros, then second row it's all tens, the third row it's all 20 and 30. So we have got this array. Just hold on, I got some error over here because I did not execute this either. Yeah, so I've got the array over there. Then I construct another array that is with the elements 0, 1, 2 in each row. All right, and here you could see that arr dot a and arr underscore b, these have the same shape. That is, if you want to see the shape of both of those, you would just do a arr dot arr underscore b dot shape. Okay, so now run this. Arr e dot shape. Yeah. So you would see they have identical shapes, and we don't need to do any broadcasting. We will get the addition of this first part of the part of our image, or you can say diagram, as the one you could see on the screen here. Okay, so no broadcasting needed in this case. Now let's move on to the second part, or you can say a second case that we are dealing with right now. So here in the second case, what we have is these two arrays. You would see they differ in number of dimensions. So let's see what are the dimensions of each array. First, I would construct that array of 0, 1, 2, and I would check the dimensions now. ARR of A. First, I would check the dimensions of ARR underscore A dot end. If I do this, What do I get? 2. Then I would get ARR. I want this array now. I want this array now. So I construct that array and then ARR underscore 2 and then again. I'm just checking the number of dimensions for both of. You would see there is a difference in number of dimension, and that is where we will have to follow the rules, or we'll have to take the assistance of the rules to do a broadcasting. All right. So what the first rule says is, just have a look at, if two arrays have different number of dimensions, in which in our case it is the same. We have different number of dimensions. The shape of one with lesser dimensions is padded with one on the left. So here the shape of one with lesser dimensions, you would see here this one is lesser dimensions, and this array in this diagram is a lesser dimension array. We have named it as ARR underscore 2. It has lesser dimensions. This is a two-dimensional array, this is a one-dimensional array. So what they are saying, the array with lesser dimension is padded with one on the left side, one on the left side of the shape. Okay, so shape of one with lesser dimension is padded with one on the left side. Now what will happen in this case is, if I check for the shape of ARR underscore 2, ARR underscore 2, ARR underscore 2 dot shape, right? Okay, it's 3 comma. Now they are asking me to pad it with 1. So the resultant shape here would be, after padding, it would be 1 comma 3. Sorry, 1 comma 3. I just added 1 on the left side of 3. All right. Now the next rule says that, let's see, if the shape of array does not match, now we are able to match the dimensions. Now the shape, we need to match the shape of arrays as well. Okay, so if the shape of arrays does not match in any of the dimension, the arrays with shape 1 is stretched to match the shape of the other array. Now in our case, we have one array that is 1 comma 3, padded, that is with the shape 1 comma 3, and we have another array. Let's check the shape of that array as well. That is ARR underscore A dot shape. Okay, so we have another array with shape 4 comma 3. What they are saying in the second rule, that whichever array has the shape 1, okay, you stretch it to the shape of the another array. That means to make this 4, I will have to broadcast this 1 comma 3, this array with dimension 1 comma 3, sorry, with shape 1 comma 3 to uh, 4 times. I would have to broadcast this array 4 times, so that I would be able to change the shape of ARR2 to 4 comma 3, and that is what exactly will happen. And after this happens, the shape, after applying second rule, after applying second rule, the shape would change to 4 comma 3. Okay. Now when the shape and the dimensions of both the arrays are equal, we can definitely perform an addition, and that is what it does when ARR plus ARR2. Now if you look at the output carefully, we get the output easily, because broadcasting is performed in the background. How it is done, that is what I was explaining with the help of the rules. All right, so it takes care, the Python takes care, Python, that is the NumPy library, takes care how to um, NumPy library takes care how to do a broadcast. You did not do anything, but then you need to understand what happened in the background. So this is how the operation works, and you still get the same result. All right, if you would have seen here in the diagram, even if the number of dimension is different, shape is different, then also you are getting this as an output. You would see here 0 1 2 has been stretched to match the shape of the another array, and once both of the arrays are of same shape, you get the same output. This blurred output is nothing but a broadcasted, this blurred part of this array is showing what is broadcasted. Now let's refer to the third case, where you have these two arrays 0 10 20 30, and the another array is 0 1 and 2. Again we will check with the rules, that are the number of dimensions different, and is the shape different. So I have already constructed that array ARR1. Okay, I will just take the shape of this ARR1, ARR1 dot shape 1, ARR1 dot name is ARR1 not defined. Maybe I have not run this cell. run arr1. See, I get the array dimensions as 2, and then again arr score dot, you have array dimensions as 1, which we have calculated earlier as well. So referring to our third part, or you can say a third case, where you have to do an addition of these two. Now the dimensions are different, all right? So again, the same rule. What the first rule says is pad the shape of array with lesser dimension with 1 to the left side. So lesser dimension to the left side. Okay. So following rule number 1, what will happen here is that we will check the shape first. Arr underscore dot shape. Okay. Arr underscore 1 dot shape. So 2 dot shape. Sorry. Okay. You would see the shape is also different. Okay. Now what it is saying, add 1 to the left of ARR. So after 1 to the left of ARR underscore 2, because it is with the lesser dimensions. Now when I do adding, what will the output be after adding 1 to the left? Shape will change to what? This shape will change to 1 comma 3. 1 comma 3. Now applying the, let's try to apply the second rule. What the second rule say is that if any of the shape is one, shape has one, all right, so you just do a broadcasting over there broadcasting is possible, all right. So we could see here arr1 dot shape has 4 comma 1 and arr2 dot shape has 1 comma 3. Now let's have a comparison from right to left. That is, as per the second rule, here we have in arr1 the in the axis 1, that is columns, we have 1, and in the arr2 we have 3. So one of them is true, so we can do the broadcasting easily, and we will what the broadcasting will do is that arr1's column will be repeated 3 times. So arr1 was what? Let's have a look at what is arr1. I'll just retype arr1 over here so that I don't have to scroll down up and down again. This was the arr1 for axis 1, that is columns. We can do the broadcasting because we have arr2 of shape 1 comma 3. So arr2 has got 3 columns, arr1 has got 1 column. So wherever it is 1, that array will be stretched or repeated, in this case to match the other, that is that has 3 columns, so it will be repeated for 3 times, all right. And for axis 0, that is for rows, if you would see arr underscore 2 has got 1, so that one can be stretched or repeated 4 times to match the arrays, so to match the rows of arr1. And after doing that, what will happen is that you would get the output that you see in the diagram. I hope the concept of broadcasting is pretty much clear. Here in this case, in part 3, we saw that we could broadcast both of the arrays. One broadcasting or one repetition was done across columns, the another repetition was done across rows. In the previous example, it was only one array that we did broadcasting, which as it was required. So it will be different situations in cases of different kind of arrays. And then there is rule number 3. If dimensions do not match, neither of them is 1. So what it says is, if there is no matching dimension and there is neither of them is 1, in the sense here broadcasting was possible because one of one of the um, one of the dimensions was at 1. But if there is no 1 here, like 1 comma 3 or 4 comma 1 in the shape, then you will not be able to do any broadcasting will fail. To give you an example, if array is of shape say 2 comma 4 and 4 comma 4, then the broadcasting will fail. It is not possible to do a broadcast. So that's all about NumPy broadcasting. I hope I was able to convey the concept.
Now let's jump in next topic.
So our first line of code, import NumPy as NP. Then I have also imported matplotlib.pyplot. So let's see how we can read an image file. So in matplotlib pyplot module, we have this function called as imread. All right. which is used to read a particular image. So I have already uploaded an image called as flowers.jpg, and I'm trying to read that here in the collab. So that's the reason plt.imread and the image name. So if I run this cell, you would see that image has got loaded here um, in Google Colab. So if I do a image and I want to see what is there in image, you would see this beautiful image of flowers. All right, and you'd see it is displayed as an ND array object. This image is stored as an array. That's the reason you get this as an ND array object. Okay, and if you have a look at how many number of dimensions are there in this image, then you get it as 3, because the images are stored in 3 dimensions, that is rows, columns, and the depth, that is the depth of the pixel value. If you are aware, a pixel is nothing but a smallest unit of um, digital image or digital display, you may call. So it contains nothing but RGB values, that is some value for red color, some value for green, and some value for blue, and those values lie between 0 to 255. All right, um, and that is denoted by the third dimension here. If you have a look at the shape, image dot shape, so you would see these are nothing but rows, then these are columns, and these are uh, the pixel values. In this third dimension, it has got r comma g comma b, these values, and each value will be between 0 to 255. Now if I check the type, as it was already displayed earlier, it is just to make sure that it is numpy.nd array. All right, now if I want to try and to do some modification into the image that we have loaded, that is flowers, what I do a image.copy, that is img.copy, because img is a variable where our image is stored, and I store it in totally a different variable because I don't want to modify the original one. Instead, I made a copy of it and I will modify. Now what I want to modify here is the is the color of the current image. So what I'm trying to do is img red, then in this position I don't want to modify anything. In the second position also I don't want to modify anything. But in the third position, where there are RGB values, I want to do some modification at index 1 and 2. So if I run this, I modified the index to index 1 and 2 to 0, and the index position 0, that 0th index position, I did not modify anything. So that's the reason you got red as a display. If I modify something else, that is if I modify say 0 comma 1 and make it to 0, that means r, that is red color, will become 0, then green, rg, yeah. So at the first index there is g will become 0, that means the resultant image should turn into blue. So let's see if it turns down to blue, and look at this, the entire image has turned to blue color shades. All right, so this is how you actually modify a particular image. Now if you are asked to rotate an image, so guys, rotation is nothing but you just need to apply a transpose function, right? When you rotate, you actually transpose from rows to columns and columns to rows. So I'm using the transpose function that is available in NumPy, and I pass an image to it, and then I, instead of writing the index at 0, 1, and 2, I want to transpose rows and columns, right? So rows and columns are nothing but these two parameters. So instead of writing 0 and 1, I've written here 1 and 0. Now this image, the original image, should get transposed. Let's see the result. And to plot that same image, I have this. I'm using matplotlib, that is plt.imShow as a function, and whatever I have rotated, I just want to display it. So let's see what is the output that we get here. You would notice that the image has got transposed. Rows have become columns and columns have become rows. So that is how you actually transpose or you rotate an image using a transpose function that is there in NumPy. Then how to increase the brightness for a particular image. you may just add some kind of constant. I have this image object. I just added a constant. uh, I just added I just added 50. That is a constant to each and every value present there in the image. Value in the sense it's a pixel value. All right. And then what is this 0 and 255? This is just to make sure that when I add 50 and something is still below 0, then it will make it to 0. If something goes over 255, it will shrink it down to 255. We need to ensure that the values are between 0 and 255. So if I run this and look at this, this is the image that you get. You will see that I increase the brightness. I'm not looking for clarity. I'm just showing how you can increase brightness or decrease brightness and so on. If you write minus 50, you may decrease the brightness. So that's how you actually do a increase and decrease in brightness. Now, how to crop an image? uh, for example, say I just want a particular part of an image. So how do I do it? I did it in strings. I did it in slicing. When I needed a part, I did it in list. Sorry. So whenever I needed a part of a particular list or string, I use slicing. Same thing we are going to use over here as well, and we will mention which till what number of rows and what number of columns are required. So let's see what is in our actual image. That is rows, number of rows and number of columns. So if you see here, if you look at the scaling over here, after the image was transposed, we have we have this image. That is, we have these rows. That is from the scaling is from 0 to 500 something, and then we have column scaling from 0 to 300. But this was after transpose. So before transpose, this was our rows. So we can give a range from 0 to 200 or 250, whatever we think. All right. So this looks like it's approximately 0 to 550 somewhere, and 0 to 350 in the rows in this image. However, in our original image, for rows it is 0 to 350, and for columns it is 0 to 550. All right. So if I want to slice, I should give range in between that. So from 0 to 250, I have an option for rows. I select 0 to 200, and for from 0 to 400, I select it for columns, and I don't select anything in the third parameter because I need all the uh, all the things that are related with the pixel values, and I just uh, try to display the cropped image by using im show function that is there in matplotlib. So if I run this, you would see a cropped image. Look at this. Now from 0 to 200, that is what I mentioned in the rows, and from 0 to 400, that is what I mentioned in the columns. That's why instead of showing the entire image that looked something like this, it is showing a part of it that is looking like this. Okay, so I hope you have got the concept of cropping an image. After that, how to save an image in over here itself. All right. So I have just defined a variable called as path, and I named and I have just given any random name that I want the image to be saved with. All right. And then I'm using function called as imsave, which is there in matplotlib, and I mention that name and which image I want to save. I want to save the image that I cropped. All right. So if I run this code, then you would see the image being saved in this current directory. Look at this. It got appeared over here, and if you open this image, it will be exact this image. That's all about NumPy. Thank you for watching.